I want to tell you about a man who saw mathematics the way most people see colors. Effortlessly, immediately, without conscious thought. His name was Srinivasa Ramanujan, and he was a clerk in the Madras Port Trust office in India. He had almost no formal training in mathematics. He failed out of college twice because he studied only math and ignored everything else. Yet he filled notebooks with nearly 4,000 mathematical formulas that professional mathematicians with PhDs couldn't prove, formulas that seemed to come from nowhere. When the great British mathematician G.H. Hardy first saw Ramanujan's letter containing these formulas, he thought it was a fraud. No one could discover these things without knowing modern mathematical techniques. But the formulas were too sophisticated to be fake, too strange to be coincidence. Hardy invited Ramanujan to Cambridge, and for 5 years they collaborated, the clerk from Madras and the Cambridge professor, producing some of the most beautiful mathematics of the 20th century. But Ramanujan was dying. Tuberculosis or vitamin deficiency historians still debate. He returned to India in 1920 and died at 32, still filling notebooks with formulas he couldn't prove but knew were true. Today, I want to explain what made Ramanujan special, not as biography, but as mathematical analysis. What did he see that others couldn't? How did his intuition work? Why did his lack of formal training help and hurt him? And what does his approach share with my own work on symmetry and conservation? Emmy Noether and I recognize in Ramanujan something rare, the ability to see mathematical truth directly without the scaffolding of proof. This is a gift and a curse, and understanding it reveals something profound about the nature of mathematical discovery itself. Before I tell you about Ramanujan's life and work, I need to know, are you watching this because you love mathematics, because you saw the movie about him, or because you're curious about genius? And more importantly, have you heard of Ramanujan before this video? Do you know his story? Have you encountered his formulas in your studies? Drop a comment below, because I'm genuinely curious how well known he is outside mathematics departments. Also tell me what you think mathematical intuition is. Is it pattern recognition? Is it subconscious calculation? Is it something mystical? I want to know what people believe before I explain what I think Ramanujan actually did. Ramanujan was born in 1887 in Erode, a small town in Tamil Nadu, southern India. His family was Brahmin but poor. His father was a clerk in a sari shop. His mother was a homemaker who sang devotional songs at the local temple. Ramanujan was a brilliant child. He memorized mathematics textbooks. He won academic prizes. But when he reached college, he encountered a problem that would define his life. He loved mathematics so much he couldn't study anything else. He failed his exams in other subjects. He lost his scholarship. He dropped out. He tried again at another college, failed again. By age 20, he was unemployed with no degree, living with his parents. His family arranged a marriage, hoping it would settle him. It didn't. He kept filling notebooks with mathematics, strange formulas for infinite series, continued fractions, number theory, partition functions. He had almost no access to modern mathematical literature. The books he did have were decades out of date. He was working in isolation, rediscovering results that European mathematicians had found generations earlier. But he was also discovering new things no one had ever seen, and he didn't know which was which. Eventually, he got a job as a clerk in the Madras Port Trust office. It paid £30 a year, it gave him stability, and it gave him something crucial: time to do mathematics in the margins of ledgers. Now let me tell you what made Ramanujan's mathematics different and why it baffled his contemporaries. Ramanujan didn't prove his formulas, he wrote them down as facts. He would write an equation, sometimes a complicated infinite series or a strange integral identity, and simply assert it was true. No derivation, no explanation, just the formula. To a trained Western mathematician, this looked like madness. Mathematics is built on proof. You don't just claim things, you demonstrate them rigorously from axioms. But Ramanujan worked differently. He saw patterns. I don't mean he noticed patterns, I mean he perceived them directly the way you perceive the color red. He would look at numbers and see relationships that weren't obvious to anyone else. He would manipulate infinite series as if they were finite sums, trusting his intuition about convergence. And his intuition was almost always right, almost. Sometimes his formulas were false. Sometimes they were true, but only under conditions he didn't specify, and sometimes they were true in ways that took decades to prove, using mathematical tools that didn't exist in his lifetime. This is what frustrated and amazed Hardy. Ramanujan would write down a formula that looked impossible. Hardy would spend weeks or months proving it, and every time it turned out Ramanujan was right. But Ramanujan couldn't explain how he knew, he just knew. In 1913, Ramanujan wrote a letter to G.H. Hardy at Cambridge University. The letter contained 9 pages of formulas, theorems about infinite series, continued fractions, integrals, number theory, no proofs, just assertions. Hardy showed the letter to his colleague J.E. Littlewood. They spent hours going through it. Some formulas they recognized as known results. Some they could prove quickly, some seemed impossible, and some were so strange they couldn't tell if they were true or nonsense. Hardy wrote back asking for proofs. Ramanujan sent more formulas. Hardy realized this wasn't a crank, this was a genius working in complete isolation. He arranged for Ramanujan to come to Cambridge. In 1914, Ramanujan boarded a ship, his first time leaving India. His first time seeing Europeans in large numbers, his first time encountering modern Western mathematics, and the culture shock was profound. Ramanujan was a strict vegetarian for religious reasons, but this was England during World War I. Food was rationed, vegetables were scarce. He struggled to find food he could eat. He was cold. England's climate was brutal for someone from tropical India. He was isolated. There were almost no other Indians at Cambridge, and he was academically overwhelmed. Hardy and Littlewood were trying to teach him modern, rigorous proof techniques. But Ramanujan resisted. His intuition was faster than proof. Why spend a week proving what he could see immediately? This tension between intuition and rigor defined his Cambridge years. Let me explain what I mean by mathematical intuition and why Ramanujan's was extraordinary. Most mathematicians work by applying known techniques to new problems. You learn calculus, you apply it. You learn group theory, you apply it. Pattern recognition happens, but it's trained pattern recognition. You see a differential equation and you recognize the type, and you know which method to try. Ramanujan's intuition was different. He saw patterns that had no names, no categories, no established methods. He would look at a series of numbers and perceive a hidden structure that connected them to something completely different. He didn't know modern complex analysis, yet he discovered formulas that required complex analysis to prove. He didn't know modular forms, yet he discovered Mach theta functions which are related to modular forms in ways we only understood decades later. How did he do this? I think Ramanujan perceived mathematical objects almost physically. Numbers weren't abstractions to him. They were things with shapes and textures and relationships. When you or I look at the number 7, we see a symbol. When Ramanujan looked at 7, he saw its relationships to all other numbers simultaneously, its divisibility properties, its appearance in series, its role in partitions. He held vast mathematical landscapes in his mind and navigated them intuitively. This is not normal. Even among mathematicians, this is exceptional, and it came at a cost. He couldn't always explain the path he took because there was no conscious path. The formulas simply appeared to him. Now let me tell you about one of Ramanujan's greatest achievements and why it shows both his genius and his limitations. The partition function asks how many ways can you write a positive integer as a sum of positive integers. For example, the number 4 can be partitioned as 4, or 3 plus 1, or 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. That's 5 partitions. The partition function p of n counts how many partitions exist for any number n. Mathematicians had studied this function for over a century. They knew it grew extremely fast, but they had no good formula to compute it. Ramanujan, working with Hardy, found an asymptotic formula, an approximation that becomes exact as it approaches infinity. The formula was beautiful and bizarre. It involved the square root of n, transcendental numbers like pi and e, an infinite series of complicated trigonometric terms. When they tested it, the formula was stunningly accurate. For large numbers, it predicted the exact partition count. This was a major breakthrough. Partition numbers are fundamental in number theory, and Ramanujan had found a way to compute them that revealed deep structure. But here's the thing. Ramanujan claimed he discovered the formula first, and then he and Hardy worked together to prove it. Hardy said Ramanujan's original derivation was completely non-rigorous, based on manipulations of divergent series that formally shouldn't work. Yet it gave the right answer. Ramanujan could see the formula was true. He could see the structure underlying partitions, but he couldn't initially justify it by the standards of rigorous mathematics. Hardy provided the rigorous proof. This became their pattern. Ramanujan would see, Hardy would prove. Let me tell you what I find most tragic about Ramanujan's story. He was dying and he knew it. By 1919, his health had collapsed. Tuberculosis or severe vitamin deficiency, he was bedridden. He returned to India hoping the climate would help. It didn't. He spent his final year in and out of hospitals, and he kept doing mathematics. He filled more notebooks. He developed what he called Mach theta functions. These are some of the most mysterious objects in his work. They look like theta functions, which are well understood objects in number theory, but they behave differently. Ramanujan wrote down 17 examples of Mach theta functions. He studied their properties. He saw patterns in them, but he died before he could develop the theory. Those Mach theta functions sat in his notebooks for decades. Mathematicians looked at them and couldn't figure out what they really were. The formulas were clearly true numerically. But what was their theoretical foundation? It wasn't until 2002, 82 years after Ramanujan's death, that mathematicians finally understood Mach theta functions. They're related to modular forms through a deep connection involving harmonic, weak mass forms, tools that didn't exist in Ramanujan's time. He saw these objects, he explored them, he wrote down their properties, and he died not knowing the framework that would explain them. This is the tragedy of intuition without the full language to express it. Ramanujan could see truths that were decades ahead of his time, but he couldn't communicate them completely. His notebooks are still being analyzed today. Mathematicians are still proving his formulas, still discovering new connections. He left a treasure map to territories he'd explored, but couldn't describe in the language others understood. Now let me compare Ramanujan's approach to my own and explain what we share and where we differ. I also see patterns. My theorem connects symmetries to conservation laws. When I see a physical system, I perceive its symmetries almost immediately. Rotational symmetry, translational symmetry, gauge symmetry, and I know instantly what these imply for conserved quantities. This is intuition, but it's trained intuition. I learned the mathematical language of groups and algebras. I learned differential geometry. I learned how to express my perceptions in rigorous formal terms. Ramanujan had raw, untrained intuition. He saw the patterns without the language. I see patterns because I know the language. Both are valid, but they lead to different outcomes. I could prove my theorems, I could communicate my results to other mathematicians in terms they understood. Ramanujan struggled with this. His formulas were correct, but his explanations were insufficient by contemporary standards, and yet I envy something about Ramanujan's approach. His intuition was purer than mine. He wasn't constrained by conventional techniques. He didn't think about whether a method was allowed or standard. He manipulated infinite series in ways that technically weren't rigorous but led to true results. Formal mathematics would say you can't do that. Ramanujan did it anyway, and it worked. There's a freedom in that, a directness. He touched mathematical truth more immediately than those of us who approach it through layers of formalism. The price was he couldn't always justify what he saw. The benefit was he saw things others missed completely. I think the ideal mathematician combines both. Ramanujan's intuition with Hardy's rigor, the ability to see patterns directly, plus the training to prove them rigorously. Most mathematicians are heavy on rigor, light on intuition. Ramanujan was the opposite, extremely heavy on intuition. Minimal rigor, neither extreme is perfect, but Ramanujan's extreme produced formulas that are still yielding insights a century later. Let me tell you why Ramanujan's work matters today beyond historical interest. His formulas for pi are used in modern computation. Algorithms based on Ramanujan's infinite series have computed pi to trillions of digits. His work on partition functions connects to statistical mechanics and quantum field theory. The mathematics of counting partitions appears in understanding phase transitions. His Mach theta functions turned out to be related to black hole entropy. String theorists discovered that Ramanujan's formulas from 1920 describe properties of black holes in quantum gravity. He couldn't have known this. Black holes weren't even theorized when he worked. Yet his pure number theory explorations touch the deepest structures of theoretical physics. This happens over and over with Ramanujan. Mathematicians study his notebooks for pure interest and discover applications in cryptography, computer science, physics. His intuition led him to formulas that encode universal patterns, patterns that appear across completely different domains. This is what deep mathematics does. It reveals structure that transcends its original context. And Ramanujan found these deep structures by intuition. He didn't know why his formulas mattered. He just knew they were beautiful. And beauty in mathematics is often a sign of importance. If a formula is surprisingly simple or elegantly symmetric, it usually means it's touching something fundamental. Ramanujan had an unerring sense for this kind of beauty. He gravitated toward formulas that felt profound, even when he couldn't articulate why. Here's what I think Ramanujan's story teaches us about mathematics and genius. First, genius is not the same as training. Ramanujan had minimal formal education, but he was one of the greatest mathematical minds in history. Conversely, many people with extensive training never approach his level of insight. Genius is seeing what others miss. Second, intuition is real and powerful. Ramanujan's formulas were correct long before anyone could prove them. His intuition accessed mathematical truth directly. This suggests truth exists independent of our ability to prove it. The formulas were true whether or not we could justify them. Third, rigor matters. But it's not the same as discovery. Ramanujan discovered, Hardy proved. Both roles are essential. You need people who see new things, and you need people who verify and systematize those things. Fourth, cultural context shapes mathematical development. Ramanujan's isolation from Western mathematical tradition allowed him to develop his own methods, but also limited his ability to communicate. If he'd had access to modern training earlier, would he have discovered more, or would it have constrained his intuition? We can't know. Fifth, some minds are built differently. Ramanujan experienced mathematics in a way most people can't. Numbers and formulas had a vividness for him that's hard for others to imagine. This wasn't learnable, it was intrinsic. And sixth, there is tragedy in being too far ahead. Ramanujan saw things that wouldn't be understood for decades. He died knowing he'd found important patterns, but unable to fully explain them to others. Isolation, whether geographical or intellectual, is painful for someone who sees truths others don't yet perceive. Let me end with what Ramanujan means to me personally as a mathematician. I also faced isolation. I was a woman in mathematics when universities didn't hire women. I was Jewish in Germany during the rise of anti-Semitism. I fled to America where I struggled to find academic positions. I know what it's like to see mathematical truth clearly and have institutional structures prevent you from sharing it fully. Ramanujan's isolation was different. His was geographical and educational. Mine was social and political. But there's a kinship. We both found ways to do mathematics despite systems that didn't support us. And we both left work that outlived the circumstances of its creation. Ramanujan died young, but his notebooks are eternal. I was fired from Göttingen, but my theorems remain. This is the consolation of mathematics. The work transcends the person. The truth you discover doesn't depend on whether you were properly credentialed or socially accepted. Ramanujan proved this more than almost anyone. A clerk with no degree produced formulas that Cambridge professors are still analyzing. If that's not a vindication of pure intellectual merit over institutional gatekeeping, I don't know what is. I think of Ramanujan when I feel discouraged. If he could produce such beauty with so little support, what excuse do the rest of us have? And I think of him with gratitude. He showed that mathematical truth is accessible to anyone with the gift to see it. You don't need permission from universities or academic societies. You need a mind that perceives pattern and the courage to follow where it leads. Ramanujan had both. He followed his intuition into territories no one had mapped. He brought back treasures, and he left them for us to understand. We're still understanding them. We'll be understanding them for centuries. That's immortality, not in fame, but in the permanence of discovered truth. Ramanujan found truths that were always there waiting to be seen, and now we see them too, because he showed us. This is what mathematicians do. We light candles in the dark. Ramanujan's candles are still burning. If this changed how you see mathematical genius and the nature of discovery, please hit that subscribe button, because I'm exploring the deepest questions in mathematics through the lives and work of those who asked them, and I want to hear from you. What should I tackle next? The story of Galois, who died at 20 in a duel but revolutionized algebra. The story of Turing, who saved millions of lives but was destroyed by his own government. The story of my own teacher, David Hilbert, and the problems that shaped 20th century mathematics. Drop your suggestions in the comments and tell me if you'd heard of Ramanujan before today. Thanks for watching, and remember, intuition sees truth, but rigor proves it. We need both. Ramanujan showed us why.